Why do all the planets orbit in the same plane? The cosmos has several planetary systems similar to ours, with planets orbiting a host star. Our planetary system is called the solar system because our sun is named Sol, which is derived from the Latin word for sun, Solis. Therefore, anything associated to the sun is referred to as solar. Astronomers discovered that Mercury, Venus, Mars, and the rest of the solar system's planets revolve in almost coplanar orbits as soon as they began to view the night sky. How is this possible? An explanation for this was required. As of today, we believe the rationale is as follows. The planets' orbits are coplanar because, during the formation of the solar system, the planets originated from a disk of dust that enveloped the sun. Because that disk of material was all in one plane, all of the planets formed in the same plane. But let's look at this more closely. Ladies and gentlemen, welcome to the world of planet formation. According to recent research, all exoplanets are unique, and there are many of them out there. Diamonds pour down on certain exoplanets. Some have an iron core, whereas others have ice cores. Exoplanets may rotate clockwise or anti-clockwise, faster or slower, and be large or small. Some of them may be livable, with immense oceans on their surfaces. Others, being so close to their host star, may be in a tidal destruction process that heats them up, resulting in severe volcanic activity. If there is one thing we know about planets, it is that they all differ from one another. They all have one thing in common. All planets and exoplanets formed in an environment known as a circumstellar disk, orbiting their host star. How is this possible? Let us start from the beginning. We'll use the solar system as an example. A star forms as a result of the dynamic collapse of a massive cloud of gas. Most likely, this massive cloud of gas was in a highly unstable equilibrium state. Even minor perturbations in the gas might cause a gravitational collapse in which the molecules became denser and denser and the cloud shrank as a whole. It seems likely that the event that caused the collapse occurred outside of the cloud itself, as the cloud was otherwise in equilibrium. Scientists have proposed that it could have been the explosion of a nearby supernova, which is a massive star that has reached the end of its life and explodes, ejecting its whole atmosphere into space. The quiet shock wave would then have provided the initial thrust to the cloud, demonstrating how the death of one star can result in the creation of another. The heat and energy from this collapse generate pressure which, as time passes and the cloud becomes dense enough, counterbalances the influence of gravity, keeping the system together. The star is born when the two forces of gravity and pressure establish a hydrostatic equilibrium. Stars are large, hot balls of gas formed by the collapse of massive clouds of cold gas. We believe that the vast majority of stars, including our sun, were born this way. What occurs next is a little more uncertain, but we do know that there is a circumstellar disk surrounding the star, and the debris is still free-falling around it. We say around because free-falling matter does not descend in a straight path to the center, but instead rotates in progressively tighter spirals. The rotation of the sun and planets about their axes, as well as the revolution of the planets and other things around the sun, are all remnants of this original vortex. At the cloud's edge far from the star, the leftover material continued to swirl around the core. The material then settled into a thin disk as a result of this spinning, which was both easy and spectacular. This is a relatively simple physics notion that we are used to. Take the washing machine, for example. You fill it with dirty clothes, add bleach, and hit the start button. The laundry has started. Now you can see the clothing rotating, essentially orbiting around the center of the washing machine. As they rotate, the centrifugal force pushes them towards the walls. However, if you look closely, you will notice that they are not being pushed in random directions. They are not scattered out at random. Rather, they rotate in a disc-shaped zone. Essentially, your garments are circling in about the same orbital plane. This shows how the stuff surrounding the sun changed billions of years ago. The material thinned into a disk due to angular momentum conservation, and some small things known as planetesimals began to form as a result of collisions. Subsequent aggregations resulted to the development of the planets we know today. Even today, the primary components of the solar system orbit our star on almost the same plane known as the ecliptic. Well done! This is the most straightforward and elegant solution to answer the basic question, why do planets in the solar system orbit in the same plane? However, our solar system is made up of more than only planets. If you look through a telescope, you may see that our planetary system is populated by smaller bodies. These include asteroids, frozen bodies, and dust. Scientists believe they are the oldest leftovers of the solar system's origin, resulting from primordial aggregations that did not grow into planets. Their more inclined orbits than the ecliptic clearly demonstrate that these entities were excluded from the main formation mechanism along the rotation disk. The majority of this old space debris can be found orbiting the Sun between Mars and Jupiter in the main asteroid belt. Asteroids range in size from Vesta, the largest at 329 miles or 530 kilometers in diameter, to things less than 33 feet or 10 meters wide. The total mass of all asteroids is less than that of the Earth's moon. Some asteroids pass in front and behind Jupiter. These are known as Trojan asteroids. Asteroids that approach Earth are known as near-Earth objects, or NEOs for short. NASA keeps a close eye on NEOs because they are potentially harmful. Space agencies are currently looking for techniques to deflect an asteroid's trajectory in order to protect our planet. There is an entire field of astronomy and engineering dedicated to planetary defense. For example, the DART mission, which launched in November 2021, will contact an asteroid on September 26, 2022, as an orbit demonstration of asteroid deflection. Essentially, DART will hit the asteroid Didymos to change its speed and trajectory. DART will be the first space mission to demonstrate asteroid deflection. We can't wait to see whether it works. Before moving on, please like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Also, make sure to subscribe to the channel by clicking the bell so you don't miss any of our daily videos. As a result, we understood that planets orbit in the same plane. Let's take a closer look at our solar system. Do they all actually share the same plane? As Earthbound people, we have used the plane in which the Earth orbits the Sun as our reference plane for the solar system. When perceived from the Earth's reference frame, the Sun seems to move around the Earth in a 23.5 degrees slanted path with regard to the spin axis. This path is known as the ecliptic. It indicates that the Earth's spin axis is 23.5 degrees tilted relative to the plane of its solar orbit. With this convention, if we position ourselves on the ecliptic, the Earth has an orbital inclination of 0 degrees, and the orbital inclinations of other solar system bodies are measured in relation to this. Mars, for example, has an orbital inclination of 1.8, but Mercury has one of 7.0. Planets follow circular orbits around the Sun as shown in this image. However, the dwarf planet Pluto has a drastically different orbit. It's extremely elliptical, orbiting the Sun in a flattened circle. Pluto's orbit is steeply inclined with an angle of 17 degrees. Pluto's unique orbit gives it some interesting properties. For example, it orbits so widely that it can swap places with Neptune and orbit closer to the Sun. The last time this occurred was on February 7, 1979. Pluto stayed closer to the Sun than Neptune until February 11, 1999. The previous time it happened was in the 1700s. Pluto's orbit is erratic due to its low mass and interactions with Neptune. This means that astronomers will have a difficult time predicting where Pluto will be in the following millions of years, as errors accumulate, and it is impossible to tell where it will be in the distant future. To summarize, what we see in the universe now is the outcome of billions of years of physical processes. On the one hand, basic physical explanations can be given to comprehend why planetary systems and other objects, such as spiral galaxies, take the shape of a disk. On the other hand, scientists understand that we live in a non-deterministic, chaotic cosmos. This means that even minor perturbations in a system might produce unexpected effects. As a result, we can see planets like Pluto orbiting in highly inclined orbits, as well as unusual features in the fabric of a galaxy or a moon-planet system. For example, were you aware that the Moon is progressively migrating away from Earth? However, the impacts of chaos can only be detected over very long time frames. I mean, chaotic occurrences occur all the time, but their impacts are essentially minor on human life timelines. This is beneficial to humans because, given our short lifespan in comparison to the duration of the universe, we may treat things as quasi-static and imagine, even for a brief while, that we can forecast the behavior of the universe. Alright folks, this video ends here. Thanks for watching. What are your thoughts about it? Please let us know in the comments below. And if you enjoyed the video, please share it, and I will see you next time on the channel.